Okay, we are recording. Once again, if you ask a question, it could be on the internet. It will be on the internet. Oh, that's interesting. So here's an array program from before. I think we'll just use the first little bit of it. And so, this is that same relationship. We're talking about an array A, and I can interpret A as a pointer because truly that's what it is, right? When we do this right here, we're allocating 20 bytes, 5 times 4, and those 20 bytes have a location. And A simply points to the first byte of the 20. And by the way, A0 is also located at the first byte of the 20. Okay, so I'm going to come back to that in a moment because how C you have to declare the types in C, and how you set up the types matters. So even though they're referring to the same memory location, in one case it's saying treat this as an integer. In the other case, it's saying this is a pointer pointing to the location of that integer. So let's do this. So the first one of these, we do at printf, the location of A, and I just want to say 0, 1, 2, 3, 4, 5. Here I'm going to put I, because that's what we're looping over, and this is where it gets tricky. This would be the value at location I. That was your quiz question. What's the value at location I? It's AI. If you want to say what's the location at AI, you would do what? The address of, ampersand. And I can just do this. A, and I'm going to put it in parentheses. And the reason I'm going to put it in parentheses is because some of these operators, they apply in different orders. And so we're trying to do two things to A. One is doing this indexing operation. One is the address of. My guess is it would work just fine without the parenthesis, but there's a whole set of rules about precedence, about which operators you do in which order, and I can't keep them all straight. So if I don't know, I just put it in a parenthesis. I'll show those rules in a future lecture. So now, of course, we have a problem. See up here? This is the no seatbelts thing. If I compiled this program, let's just do it. Let's do it. Actually, I don't think it will go wrong. I'll say gcc array.c and loop, and it gives me the location of 21 integers. Of course, I only declared 5. So all of these locations, let's look at the good ones first. 80, 84, 88, 8C, 90. I have every right to be going and changing the values and reading the values of those 5. Down here, no seatbelts. C is happy to tell me what the memory locations are here. Do I have any right to touch them? I do not. Okay? I will get in trouble. So, and the reason that we started accessing stuff outside A4 is simply because in my loop counter from a previous example it said 21. So there's that. Okay, so now because I've changed my code, when I run this, I'm now restricting myself to only the memory locations that I have a right to be in. Now, hopefully this makes sense. A0 is at 80, which is the same as the front of the array, also 80. A1 is at 84, A2 is at 88, A3 is at 8C, and 90 is at A4. Now let's get into trouble. Okay, well, no, before we get into trouble, any questions about this? Yeah, Krista?
What is the sequential order of 0, 4, 8C?
Yeah. So this is up to the compiler, right? And so the compiler has decided we're doing array accesses, and this actually makes sense to me that it wants it to be ascending because of the way that you can access array elements in other contexts, and we'll get to that. So it's decided that even though we saw in a previous example the stack is counting down, it decided to put A0 at the smallest thing, because when you want to access A1, it wants to be adding to it, and A2 to be adding to that. And so there's some rules in there that we'll get into in the future about how it's doing adding, and that's why it wants A0 to be the lowest number. So these are, so it's going to start, I think the stack is going to start at 7 and a bunch of Fs. And you can see, before we even get into main, some other memory has been allocated for other purposes. So in a C program, there's stuff that happens before you get to main. You could be a C programmer for a long time before you do anything where you write code that executes before you get to main, but it's certainly possible. And so the reason we're not seeing a whole bunch of Fs is because someone else did some stuff with memory before our program even ran, and the compiler slipped that in for us. You know, when we call printf, it works. It did some initialization somewhere so it would work. But whatever, you know, it decided probably that 90 was the first address it had a right to access, and then it put A0 at 80, and then counting up 4, 8, and then C, and then 90. So again, hexadecimal addresses, that's part of the letters. Brian?
So does note that when A0 is the lowest one, does that to get to like the farther indexes, when you go to A0, when they get to like A2, that's when you get A0 first?
Yeah, so there is some work happening there. So I'm not going to try to repeat the question, but let me, because it's hard on the video and everything. But let me say, when you are actually accessing A2, it is taking the address for A0 and it's adding 8 to it. And then it's saying that's the memory location. So one of the things I said earlier is one of the things I love about C is everything I write corresponds to a small handful of assembly instructions. In this case, it's more than one, right? Because it starts by saying, where's A? And then it says add 2 times 4 to that, and that's the memory location I want. So there was a few assembly instructions that would happen before it actually did an assignment or a lookup or something like that. But yes, that's exactly right. It's going to the pointer, and then it's doing some arithmetic to figure out the location of where it really wants to be. Nathan?
I don't know if this is obvious or not,
Okay.
but I just want to clarify. Let's say I have a subarray B that contains like 2 of the elements within A. C does not allocate any new memory.
Yeah, so the question is about subarrays, and so subarrays, C has built in a notion of an array, and you might go and take a subrange and say, I'm declaring that here's another array you can work with, and you know it's part of a large array. That's about it. Now there's some extra stuff where you can get like pointers to pointers, like arrays, nested arrays, multi-dimensional arrays. We'll get into all that, but not yet. So, okay, I do want to get into trouble, and then I'm going to stop this video. So let's get into trouble. So what is the address of A? Or of I, I'm sorry. Address of I is %P. Okay, so I is at B78. So it's interesting, you know, that is, so A is at 80 and I is at 78, which means it's actually 2 integers away, right? So it would be occupying the byte 78, 79, 7A, 7B. It looks like nothing is being placed at 7C, D, E, F. Let's just try putting something in. My guess is that if we do that, it's going to put J in those bytes that it didn't fill in. So now it did not. It put I at 7.8 and J at 7.4. So it's not letting us put anything in 7C. Okay, I'm still going to get into trouble here. I equals 5. I'm going to say A of minus 2 equals 3. Value of I is %D. I. So, my hope, and it will ruin the video if I'm wrong, is it's going to print out I as 3. Okay, let's try it. So we've gotten a warning saying you really shouldn't be going to a negative number, but it's just a warning. And there are contexts where you actually want to go to negative numbers, but not this one. And the compiler's smart enough to tell you that. And if we run it, I is indeed 3. So let's see what happened here. So first off, we know that A is at 8, 0. So then A of minus 2 is going to 8, 0 plus minus 2 times 4. And the same way that A2 went to A0 plus positive 2 times 4. Well, 8, 0 minus 8 is 7, 4. That's the location of, is 7, 8. That's the location of I. And so even though I assigned a value of 5, this was assigning a value of 3 to the exact same memory location. And when I print I, it's no longer 5 because it's been overwritten with a 3. Okay, so the thing I want to say, I'm going to stop the video and then I'll take the question. The thing I want to say is, when you are writing to places that are outside your allocation, weird things can happen. If you want to do it in a predictive way like we did, you'd have to look at memory addresses and kind of design a special experiment. But if you are going outside the bounds of an array, you can get just weird behavior. There's no seatbelt. Okay, I'm going to stop the video.